Hello, in this video we are going to talk about infinite series and learn about a couple of different types and how to prove whether they converge or diverge. Specifically, we're going to look at geometric series and telescoping series. But before we talk about those types of series, we've got to figure out what is a series. And a series is a sequence of partial sums. And I know it sounds like a mouthful, but really what we're doing is we're taking a sequence, and instead of just listing out the terms of the sequence, we're going to start adding the terms together. Okay, and they're partial sums so for instance, with the first term, it's just going to be the first one. When I get to the second, well, I'm going to add the first two terms of the sequence together to get the second term of the series. For the third term of the series, which that should be S3 right there, not S2, I add the first three terms of the sequence together to get that one. And I can keep going like this for as long as I want to get terms of my series. So the nth partial sum is what we would call Sn, and that would be the sum of the first n terms of the sequence. And I can write that using the summation notation, which is nice and compact. So it's AK, where K starts at 1 and goes to N. Okay, that K is referred to as the index. So if you're referring to that, the index, I'm talking about those K values there. Now, I can take this a step further, and let's say I wanted to know what happens as N approaches infinity. So I want to keep adding terms, an infinite number of terms together. So this would be the limit as N approaches infinity of the nth partial sum. This middle one here is written as the limit using the summation notation. Okay, so they mean the exact same thing. And this last one is the most compact notation for a series, the one we typically use, where the index starts at k equals 1 and goes to infinity. But all three of these statements mean the exact same thing. Okay, so usually when we're talking about series, which we're going to spend the next 2 units talking about series, we want to figure out whether a series converges or diverges. Is it approaching a particular value? If I keep adding more and more terms of the sequence, am I approaching a particular value or not? And so there's going to be a lot of different ways that we learn to prove whether a series is convergent or divergent. And it's all going to depend on the type of series or the characteristics of each series that will tell me which convergence test I want to use to prove convergence or divergence. The simplest way to prove that a series converges is to simply take the limit of the nth partial sum. If that approaches a particular value S, then I can say that the series converges. Okay, if I get a real number here. So the nth partial sum has to approach a real number as n approaches infinity in order for a series to converge. If this doesn't happen, so let's say the limit doesn't exist or it approaches infinity, then I would say that the series diverges. And those are really my only two options here until later we'll learn about absolute convergence, but that's a ways down the road. Okay, so let's look at our first type of series, and we'll use this limit of the nth partial sum to determine whether a telescoping series converges or diverges. So a telescoping series is a series whose partial sums eventually only have a fixed number of terms after cancellation. So usually I'm looking for like two terms that are subtracting when I'm trying to identify a telescoping series, so that terms will start canceling. If I start listing out all the terms that are being added together for the series, if things start to cancel out, then I'm probably dealing with a telescoping series. So we want to look for something that has a difference of two terms, or that can be written as a difference of two terms inside of your summation notation. And just like we said in the last slide, if I take the limit of the nth partial sum and I get a real number, then I can say it converges. So really what our plan is with the telescoping series is we're going to figure out what that nth partial sum looks like. If I go out to a particular n value and I cancel out all the terms that cancel, whatever's left over, I want to take the limit of that as n approaches infinity and see what I get. So let's look at an example of this. Okay, so I have, too far. So I have this series here. We want to determine whether this series converges or diverges. And it has the subtraction of two terms that look pretty similar to each other. There's just some different constants in here. So that is like the perfect setup for a telescoping series when I see that kind of thing happening. So the first thing I'm going to do is I'm going to write out that I'm going to call it the kth partial sum here, since our index is k, and look for a pattern for cancellation. Okay, so I'm going to start plugging in values for k into these terms. So if I plug in 1, I get 2 in the root of this first term. And so that's 1 over root 2 minus, and then 1 over root 4 here. I'm not going to do any simplifying, even though I see some perfect squares in there. I'm really just looking for when do things cancel with other terms. So don't worry about simplifying here. Okay, so I plug in, here's k equals 1 in the first set of parentheses, k equals 2, k equals 3. And then I start looking for things that cancel. And the first thing I see that cancels is this 1 over square root of 4. It cancels. And so I can assume if I were to keep going here, it looks like the 1 over square root of 5 would cancel with the next term that's not written. And then 1 over 6, square root of 6 would eventually cancel, and so on. The things that wouldn't cancel is 1 over root 2. There's nothing that's going to appear in this pattern that looks just like that. Same thing with 1 over root 3. And you may want to write, I only wrote the first 3 terms before I went to a general term. You may want to write more terms than that in order to figure out where the cancellation is happening and what terms survive the cancellation, what doesn't get canceled out. If I come to the end here, following that pattern, the 1 over root k is going to cancel, just like the 1 over root 4 canceled in this third term. And the 1 over root k plus 1 is also going to cancel. So these are the only 4 terms that are not going to cancel in the kth partial sum of this series here. Now that I've determined that, it's the hardest part on this one, I'm then going to just take the limit as k approaches infinity for this. And just looking at this, I know that these last 2 terms with the k's, the denominators are getting infinitely large. So those terms are going to approach 0. And then the first 2 terms are just constants. So this limit is just going to be 1 over root 2 plus 1 over root 3. Now, that's not the prettiest number in the world, but it is a real number. So I can say that this series converges. And it's really important whenever you're proving convergence of a series that you state which test you are using. This is something I'm absolutely looking for every time you solve a convergence problem. So my final statement here is the series converges, and I know that by the telescoping series test. Okay, we want to hit all those buttons as we write out our solution, our explanation of how we determined that the series converged. Okay, the other one we want to look at is geometric series in this section. A geometric series looks like this. If I look at the terms, they're just increasing by a factor called the ratio. So each term I get from multiplying the previous term by the same number over and over again. So maybe, 1/2, then 1/4, then 1 to the 8th, and so on. So I'm just multiplying by 2 or 1/2 each time. And so that will be a ratio. The key to these is noticing that pattern and then determining what that ratio is. So if that ratio, if I take the absolute value of it and I get something less than 1, then I can say that the geometric series converges. And I can even find the sum. There is a formula for this one. If I take a over 1 minus r, where a and r are coming from the general term here, that will be the sum that this series is approaching. If the absolute value of r is greater than 1 or equal to, then the series diverges. Now, some notes on this. A, sometimes it can be kind of tricky to figure out what A is. Really, A is just the first term of the sequence. So if I plug in whatever the first K value is down here into this and simplify, that will be my A value. And then R, if you're having trouble identifying R, you can always take 2 successive terms and divide them, and that will give you the ratio as well. Other note is there are some variations on this. K doesn't have to start at 0, and the exponent can be something a little more complicated, like a k minus 1 or a k plus 1, and it's still going to work as a geometric series and this geometric series test. Okay, so let's do an example with this one. So here I have a geometric series. So they were kind enough to give it to me in summation notation, and I can clearly see that it fits that format. I have some constant out front and then 2/3 to the nth power, where n is my index. So that is a geometric series. And so I'm going to identify it as a geometric series, and the absolute value of r is going to be 2/3. That 2/3 is less than 1. Okay, so these are the requirements of the test. You want to make sure you're stating this part here. And whenever the ratio is less than 1, we know that the series converges. So it's pretty quick once you identify this as a geometric series to prove convergence. And so that statement there was enough to be able to conclude the series converges. And of course, I want to say what test I'm using, which is the geometric series test. Now, I can find the sum on this one. Most of the tests, you're not going to be able to do this, but this one I'm going to go ahead and find that sum. So if I wanted to find the sum, the ratio is 2/3, and a, the first term, is 4. If I plug in 0 to n, I get 4 times 1, so I get 4 for the first term. So plugging that into the formula, a over 1 minus r, I get 4 over 1 minus 2/3, which I can stick into a calculator, and I get 12. So the sum of this series is 12. Okay, so we did a telescoping, we did a geometric. Here's a couple more examples for you to try on your own.